Welcome, welcome, welcome to Correct Science. Today we are going to solve some questions on electrostatics. Let's look at the questions. So, a positively charged piece of plastic exerts an attractive force on an electrically neutral piece of paper. This is because A. Electrons are less massive than atomic nuclei. The electric force between charged particles decreases with the increasing distance. An atomic nucleus occupies only a small part of the volume of an atom, and a typical atom has many electrons but only one nucleus. You can pause the video and try it on your own. The answer is B. Why is that so? Okay, so first of all, we know that the plastic is positively charged. The plastic is positively charged. Now we have a neutral piece of paper. This neutral piece of paper consists of atoms, and these atoms, has positive and negative charges. So the positively charged piece of plastic can actually polarize the piece of paper. Now in doing so, the negative charges will be closer to the positively charged piece of plastic, while the positive will be further from the positively charged piece of plastic within the same paper. So since the negative is closer, the attraction will actually be greater than the repulsion between the positive sides of the paper and the plastic. Because we know electric force decreases with increasing distance. So there will be a net attractive force because of a stronger force of attraction due to a smaller distance between the positive plastic and the negative side of the polarized paper. Thank you. Next question. 3-point charges lie at the vertices of an equilateral triangle as shown. All three charges have the same magnitude, but charge 1 is positive, that's positive Q. Charges 2 and 3 are negative. The net electric force that charges 2 and 3 exert on 1 is in which direction? So first of all, we are happy that it's an equilateral triangle, so we know that the distance will not be a problem here because it's equal throughout. But now we have to find the net force on charge 1. So they are both 2 and 3 are negatively charged, and so in relation to charge 1 there will be a force of attraction. The negative charge will attract the positive charge towards itself. So this will be the direction. Now, if this is the direction, then we know that if we were to extend it small to get a parallelogram, then the diagonal can actually represent the resultant. And looking at this very well, the diagonal is in the positive x. So our answer is definitely positive x direction. Very simple. Next one. 2-point charges and a point P lie at the vertices of an equilateral triangle as shown. Both point charges have the same magnitude Q, but opposite signs. There's nothing at point P. Now we are told to find the net electric field that charges 1 and 2 produce at point P, specifically the direction of that net electric field. So now we know that for a positive charge, electric field lines are away, and for a negative charge, it's stored it. So it will be toward it here, and to be away from the positive charge. To be away from the positive charge. So when we actually construct a triangle. We have vectors now. We place them tail to tail. We see that this is the starting point and this is the ending point. So we can connect with this. And now, pardon my drawing, we clearly see that if this is the starting point, following the arrows, then it will be in the positive y direction. Positive y direction. Next question. 3-point charges shown here lie at the vertices of an equilateral triangle. The electrostatic potential energy of the system of 3 charges is positive, negative, 0, or you think maybe the information provided is not enough to decide. Let's look at it together. So we know that electrostatic potential energy will be equal to U equals 1 over 4 pi epsilon naught. I mean in vacuum, sigma Q1 Q2 over R, where R is the distance. So I'm just using Q1 Q2. It could be, let me see, Qi Qg, depending on the number of charges present, and Ri Rg, so the different distances. But here the distances are equal because it's an equilateral triangle. So it means U be equal to 1 over 4 pi epsilon naught. Let's represent that by K, multiplying the bracket. First of all, considering charge 1 and charge 2, it will be Q1, which is Q times Q. So Q squared over R. Then now considering charge 1 and 3, it will be Q times negative Q. So that will be minus Q squared over R. And considering charge 2 and 3, it will be Q times negative Q. So you are going to get minus Q squared on R. Now when you actually do the evaluation, this goes to 0 and you are left with negative KQ squared on R. Evidently, the value is negative. Value is negative. Very simple. Let's look at this one too. Consider a point P in space where the electric potential is 0. Which statement is correct? A. A point charge placed at P would feel no electric force. B. The electric field that points around P is directed toward P. C. The electric field that points around P is directed away from P. D. A point charge placed at P will not alter the electrostatic potential energy of the system. And E. Not enough information is given to decide. Let's see if information is enough or not. So we are saying that the electric potential V equals 0. Now, they are saying which of these is correct. The first one is saying there will be no force at P. Can we really say that? No, we can't just conclude that way. That because the electric potential at that point is 0, there will be no electric force at that point. Because we know that electric field is equal to negative dV dr. So if a point charge is placed at P, and we know that the force exerted will be QE, right? Now, V being equal to 0 doesn't mean that E is necessarily equal to 0. No, it's like the same way velocity is 0 at the maximum point or maximum height in projectile motion, but the acceleration is not necessarily 0. The same point here. So this is out. It's not necessarily correct. Now, the value of the electric potential doesn't actually give us the direction of the electric field. So just both B and C are out. What about D? Let's see if it's true. So we know that the change in the electrostatic potential energy here will be equal to the charge times the change in the electric potential. But now, at that point, it's actually QV. At that point, we know that V equals 0. So definitely, change in U will also be equal to 0. Therefore, the answer is D. The answer is D. Thank you. This question as well. Where an electric field line crosses an equipotential surface, the angle between the field line and the equipotential surface is A. 0, B. Between 0 and 90 degrees, C. 90 degrees, D. Not enough information given to decide. Is it really enough? I think so. So this one is a fact that it's 90 degrees. But why is it 90 degrees? So we have to first know what an equipotential surface is. An equipotential surface is a surface on which the electric potential is constant at every point, meaning no work is required to move a charge along it. Why? So we know that the work done will be equal to Q times change in V, right? Now, if the electric potential is constant, then it means change in V is actually 0. There's no change in the electric potential. Therefore, the work is actually 0. Now, we also know that work is equal to the integral of the dot product of force times the dot product of force and an infinitesimal displacement. So the line integral of the dot product of force and an infinitesimal displacement on that equipotential surface. Now, the force is also equal to QE. So Q is a constant, so we can bring it out. ds. So we are saying that this is equal to 0 for the equipotential surface. Now for this to be equal to 0, and we know it's dot product, that means the angle between them, the cosine of that angle should actually be 0. When we check our calculator, that's 90 degrees. And now we know that the infinitesimal displacement is on the equipotential surface. So it means the electric field is perpendicular to that infinitesimal displacement. Thus, we justify our answer that is 90 degrees. Thank you very much for watching this video.